Witkowska. I'm the founder of Ladies Build with AI, and today I'll be the chair of this track, so welcome. And just a quick note for those of you who weren't at the main stage opening today, next year is actually the World Summit AI's 10th anniversary, so the team have already started planning what is sure to be the biggest yet. So whether this is your 9th World Summit AI, or maybe just your first one, the fun actually doesn't stop here at the summit. Inspired Minds have launched the Inspired Minds online community hub. It's unlocking access to premium on-demand content from podcasts and presentation to backstage interviews. So members will not only benefit from unique discounts, CPD points, training, and development and more, but today it's also part of being the AI community who can connect, share, and shape the future, which is so important. So the Hub is a unique platform to open up a world of possibilities for you at the highest level of the cutting-edge tech. Booking is also live for 2026 in Amsterdam, and space will be limited. So please scan the QR code to get involved in the Hub. And why not get in first and secure your space already for next year in Amsterdam? So we'll get started with the track with the first presentation of today. And we're going to look at AI Beyond the Lab, Ocado's real-world application. And our speaker for this one will be James Humphreys, VP Engineering, Logistics, and Supply Chain from Ocado Technology. So over to you, James. Thank you.
Thanks very much. Hello everyone, I'm James Humphreys. I'm VP of Engineering at Ocado Technology. For the last 3 years, I've been working on embodied AI, more specifically, the fully automated robotic picking systems in our warehouses. And I'll talk about that in more detail in just a moment. First, just a very brief word about me before we get started. My background is kind of in the dark days of AI. Back in the AI winter, I did my undergraduate degree in artificial intelligence. I then followed that with 2 years of research in computer vision. And I joined Ocado way back in 2007. And I wrote our route optimization engine, which is a piece of an algorithm that calculates the optimal way of getting all of our orders to people's homes in 1 hour windows. So it's a variant of the traveling salesman problem, if you're familiar with that. So I absolutely love this work, right? Because on the one hand, very, very complex algorithm, took a lot of research to get it right. And on the other hand, it delivered a huge amount of value for the business. That's a fantastic combination, and it kind of set the scene for my whole career. But I left Ocado. I went to work for BP Trading in London, where I built teams working on optimizing BP's global logistics and trading. And in my spare time, though, whilst working, I helped a friend get a mapping startup going called What 3 Words. And I wrote some of the initial algorithms to get it off the ground, and the compression algorithms to get it on people's phones and so on. But I was eventually enticed back, this led to a CTO role. So I spent several years at What 3 Words kind of growing it to its present strength. But eventually I was enticed back to Ocado, and that was because I was given an offer that was so exciting I couldn't refuse it, and that was to work on Ocado's on-grid robotic pick. So for those of you who don't know, Ocado started way back in the early 2000s, and we're an online grocery store. So people shop online for their groceries, we would pick and pack them, and then we'd deliver them to people's homes in a 1 hour time window. And this is what it looked like in the very early days, very, very manual, essentially picking with trolleys, and we knew we needed to automate it. And we've been on a technology journey ever since then. Now this was the first iteration of our warehouse, like already a massive, massive step forwards. This was in the early 2000s. I'm going to spin ahead another decade, and it brings us to our modern warehouses, which look like this. We reinvented these warehouses completely from scratch. And the bots you see behind me are traveling across the top of our grid. And the grid is a 3-dimensional cube full of storage bins, and those bins are full of groceries. And you can't see it in this picture really, but the boxes are actually stacked 21 deep. So this is very 3-dimensional, very, very dense. And the bots travel across the top of that grid. They can pick up boxes, kind of put them in their bellies, travel anywhere else on the grid, and then drop them off. However, so this is a fantastic bit of automation, of course, right? We've cut a lot of labour moving goods around, but to pick a customer's order, we still needed to bring those storage bins and the basket to the same location to a human being who would then do the final act of actually picking an item from the storage bin into the customer's basket. So that's still a significant portion of manual work that we can go after to make things more efficient. And that's where our next evolution, on-grid robotic pick, comes in. So this is it behind me. It's a 6-degree of freedom robotic arm, and it uses a suction cup to pick up items to pick and pack a customer's order. And the arm itself, some of you might recognize, is an off-the-shelf universal robot arm. We have cameras for seeing, we have one on the wrist and one on the elbow, and we also have a force torque sensor, which gives the robot a sense of feel, effectively. Now that's pretty off-the-shelf hardware. There's not a lot of complexity in the hardware. And that meant that we had to build a much more complex machine learning system to cope with that simpler setup. But it's much, much more scalable. So we gave ourselves quite a tough task. You'll notice the arm is built directly on the grid. That's very, very efficient. But it is also very, very complex. And it's particularly complex for two reasons. One is the arm actually shares its space with the bots that are bringing the work. You can actually see it right there. It's dropping off work for this arm to do the picking. Now that means you've got to coordinate in real time to prevent collisions. And then secondly, humans can't go on this grid. So our tolerance for failure is very, very low. That means we can't intervene physically to fix things. So we have to do everything remotely, and our system needs to be incredibly robust. I want to give you an idea of the picking tasks that we're dealing with. And this is a top-down view of what the inside of those bins looks like. So this is a huge variety of goods, anything from hard cans of beans, we've got soft items like milled Yorkshire puddings, and then we have bruisable items like apples. So very, very tough. In fact, it's anything you could buy in a grocery store. That's up to 50,000 different types of item. Secondly, it's a chaotic environment. These are not neatly arranged, right? So you can't hard-code positions in any way. And the only way to solve, actually, one more thing, which is, this is not a realistic picture. This is a perfect warehouse. Like in a real-world warehouse, these items come in boxes. Those pieces of those boxes sometimes end up as trash inside the totes, inside the bins. Some items get damaged. You might end up with the wrong goods in the wrong bins. And all of these things that happen in real warehouses we have to deal with. So the only way to deal with that complexity is machine learning. Right, to deal with that kind of long tail of very difficult tasks. So that's very good context, but now I'm going to cover the actual act of picking itself, which is where the real AI magic happens. I want to quickly walk you through the machine learning journey that we took, and I think there were two really big generations. Our first generation system was a more traditional open loop approach. This is where you look, plan, and then you act. So the robot would look inside the tote with a camera, it would then take a picture of the contents of the bin, it would then use traditional image segmentation to find the objects, it could then plan a precise location to do the pick, and then act and do the pick. So it was a hybrid system, right? We made very heavy use of machine learning in terms of computer vision, but at the end of the day, we were still using computer code to control the system. We also gathered data for every single pick. We knew whether the pick was a success or a failure, because we know the suction cup pressure, for example. You can use that data to feed back into the system and constantly self-improve. And so we ended up with a very, very powerful system and pretty successful, but it was still hybrid. It still had code, which meant that every time you want to deal with those corner cases, you end up adding a bit of if statement, effectively. Now those if statements kind of build up over time, and it becomes impossible to deal with all those scenarios that I mentioned earlier. So that leads me very neatly to our second generation. But before we talk about that, I just want to introduce our teleop system. Now, as I mentioned, the system wasn't perfect, of course, and to recover from errors, we needed a teleoperation system. Right? We needed a way to recover items using pilots. And this is what you see behind me. The person on the right has VR handsets, they're controlling the robot on the left in real time, and here they're in the lab, but they can be separated by any distance. And in fact, in production, they're separated by constants. We knew these teleop pilots were fantastic. They could outperform the system. And we're also aware that behavior cloning was a massive up-and-coming area. So what we did is we collected all this data. We watched human pilots complete tens of thousands of picks, and we gathered all that data, and we trained a neural network using this data to mimic the behavior of the pilots. And we collected petabytes of data, which required a completely bespoke training system. But what we ended up with was something slightly magical. We ended up with a fully end-to-end machine learning-driven picking system, which means you've got pixels going in at one end, and you've got robot control at the other end. And all of your behavior is now encoded in network weights, rather than if statements. The system was closed loop, which means it reads over 10 frames per second, so it's extremely responsive and adaptive. And its performance just blew us away when we first tried it, and we transitioned entirely to this second generation approach. Now I have a video I can show you of it picking, and this video is taken from the wrist of the arm, and you're going to see what the actual machine learning model sees. So this is the system picking real groceries in a real warehouse, and most of the picks are flawless, but I've intentionally chosen some recoveries. Now you'll notice the pick motion is very fluid when it's going in for the pick, and that's the closed loop nature. It's the fact that it's adapting absolutely continuously to what it's seeing, rather than planning. It's not stopping to plan at all, it's simply reacting. Now interestingly, it's learned some recovery behaviors without them being explicitly coded. This is really interesting. This really surprised us when we saw it. For example, there are some items that get stuck sometimes that it can't pick. I think this is a very good example. You could miss it if you blinked. It's very, very quick. It missed the first few attempts, it went straight back in. That isn't explicitly coded. That's something it's seen pilots do. It knows it works, and now it does it. So we didn't have to code that. It can also manipulate items before picking them. It sometimes has to wriggle things loose from the packaging, so it kind of pulls things free. That's a very good example. It picked up 2 loaves of bread there, spotted it, put it back immediately. It didn't even stop. That's the key bit. Right, it's doing it again here, and it goes back in for one single pick. The system also learned to generalize. Amazingly, we didn't have to train it to pick every kind of item. This is something we worried about initially. But we found that we've trained it on so much data now that if you give it a completely new item, it will go in there and just pick it quite happily. Oh, it's a very good example of manipulation. So it's just pushed the item over before it went in for the pick. There's another one coming up here, which is, it knows it can't pick it from the top, right? Because it wouldn't get a full suction seal. So it knows, it's learned to go and just knock the thing over before it goes in. And then finally here, that's picking up trash, right? So it's probably quite hard to see actually potentially, but there was a transparent sheet there that it picked up. It realised and then went and put it back. So hopefully you'll agree that's reached a very high level of robustness, right? Not only robustness, but also speed, because it's completely fluid. The thing keeps going. But OGRP isn't just a demo. It's real-world robotics, right? That's why we're here. And it's operationally profitable in real warehouses around the world. So we're live with 4 partners. We are in North America, the UK, Spain, and Japan. And in one of our best warehouses, we're picking well over 1 million picks per week. We have something like, I think it's about 140 arms to 200 arms live. I think 200 are installed, about 140 picking right now. And that should rise to about 500 by the end of the year. So we are on a bit of a hockey stick growth right now. And to give you a sense of like the amount of picking it's doing, we're picking up in our best sites, we're picking over 40% of all items that go through that warehouse are completely robotically picked. Obviously, we want to go higher than that. We think we can go well over 50%, and we're looking at new machine learning models to do that. Before I leave, I just want to leave you with 5 things that I think took us from being a demo to being a very successful product. And the first thing was keep an eye on the commercials. So we built a cost model and we stuck to it rigidly. We wanted to get a very good sense of what does this thing actually cost to run production for real. Every time we pick 2 items instead of 1, that costs us money. And we were relentlessly led by that. Secondly, we embraced multidisciplinary teams. You're going to need amazing hardware people, amazing software people, and machine learning people as well. And they are motivated by their common goal, rather than their common crafts. So you need to bring those people together, particularly at the prototyping stage. I would productionize as early as possible. This is probably the best lesson, actually. Something that works in the lab may well not work in production environments because there's so many of those long tail things that happen that you didn't expect. Don't rush to automate. This is a bit of an ironic one to put on here, perhaps. But there's something about just eyeballing the data and getting a real good sense of what's happening in the real systems. So don't automate everything. Sometimes you just need to eyeball the data. And fifth, I would say, think like a startup. We, Ocado, are a very big company. We had to be scrappy. We had to bend the rules. We had to kind of push the boundaries, and that meant kind of sometimes a little bit of asking forgiveness and pushing the boundaries a little bit to make sure that this didn't just stay a machine learning demo, but actually became something very successful. And yeah, so that's 5 things that I think helped take OGRP from just being a demo to now being what I think is one of the most successful and advanced picking systems of its type in the world. I'm supposed to have a last slide. Thank you.